Section 3.3, Systems of Inequalities. So here is an inequality love note. You can go through and solve it, figure out if you know what it says. You don't have to wait till Valentine's Day to express your love for someone through mathematics. So continuing on. A system of inequalities. Basically, this is a system of inequalities. We just have more than one inequality. And I want a value for x and y such that x plus 2y is less than or equal to 4 and 2x minus y is less than 5. So I want both of these inequalities to be true. Well, if I want to find coordinates that would make both of these inequalities true, I need to know something about graphing inequalities. So let's just take the first one here. If I want to graph x plus 2y is less than or equal to 4, there's a couple different ways I could graph this. I could just think about graphing the line x plus 2y equals 4. So what if this were an equal sign? I could graph this using the intercepts. So if I plugged in 0 for x, this would go away. 2 times what is 4? That would be 2. So the point 0, 2 would be on this line. If I plugged in 0 for y, x is 4. So because this is in standard form, I could certainly graph that line, finding the y and x intercept. But remember, this actually wasn't an equal sign. This was a less than or equals to sign. So if I think about 0, 2, 4, 0, okay, so these would be points that were on that line. If my symbol is less than or equal to, I'd actually want to go ahead and just plot this line up 2, back 4. Okay, so there's my original line x plus 2y equals 4, but I want this to be less than or equal to 4. If it's less than or equal to 4, I want to shade everything that's less than this line. And the equal part comes into any points on this line would make x plus 2y equals 4. So anything beneath, x plus 2y should be less than 4. Any points on the line, x plus 2y equals 4. So that's really the first inequality graphed. Could I also take this equation and solve for y and rewrite it in slope-intercept form? Yes, I could. So maybe you're thinking, well, I'd rather do something like this. Subtract x, divide everything by 2. That's perfectly fine. That is this line. Your y-intercept's 0, 2. Your slope is -1/2. So now let's look at the second line. So if I wanted to graph that line 2x minus y equals 5. So second equation, let's just look at if this were 2x minus y equals 5, I maybe would solve for y here, or I could find the x and y intercepts. Same thing if this is 2x minus y is less than 5. I'm just going to go ahead and solve for y, rewrite this so it looks like it's in slope-intercept form. Okay, so I have the opposite of y is less than, subtract 2x from each side. And then I have the opposite of y, so multiply or divide each side by -1. If I multiply each side by -1, careful, I have to flip the inequality. And this second equation, or inequality here, is really the same as saying y is greater than 2x minus 5. So if I want to graph that inequality, I'd actually think of, well, what does the line y equals 2x minus 5 look like? That would have a y-intercept of -5, and then your slope is 2, up 2 over 1, up 2 over 1. So here is the line y equals 2x minus 5. But I actually want to graph the inequality. Y is greater than 2x minus 5. Now, notice this is not greater than or equals to. So on those points that I just kind of drew, I do not want to connect it with a solid line. I actually just want to connect this with a dotted line. Any points on this line would be where y equals 2x minus 5, and I don't want that. I only want values where y is greater than 2x minus 5. So if I want anything that's greater, I would shade above. Now maybe you're looking at this and you're not really sure which half is above. So here's my dotted line, and I want to shade half of it. This half would be the greater than, or the above part. If you're not sure which side to shade, notice that I've shaded the point 0, 0. So if you're not exactly sure, a good check would be just plug in a coordinate. Here 0, 0 would be pretty easy. So if I plug in 0 for x and 0 for y, is 0 greater than 2 times 0 minus 5, or is 0 greater than negative 5? Yes, it is. So this point should have been on the half that I shaded, and it is. Then I know I've shaded the right part. Now let's look back at the system as a whole. So if I look at the overall system, I only want coordinates that make both of these inequalities true. Well, which points on my graph make both inequalities true? That would be this region that's shaded with the teal and the purple. So I'm actually going to get rid of everything that does not kind of have that double shading. So everything up here is going to go away. Everything down here is going to go away. That purple part only made the first inequality true, not both inequalities true. And then this would be your solution space. So anything in here is a solution. If I have a solid line, I'm including those points. That's that less than or equal to part. If it's a dotted line, I'm not including anything on that line. That's the less than part. So this is my solution set. Any point in that region should be a solution. For example, this point, negative 8, 1. That should be a solution. What does that mean? Well, if I plugged in negative 8 for x and 1 for y, that should make the first inequality true and the second inequality true. If you actually went through the work of plugging in negative 8 for x and 1 for y, this would be the first inequality, that would be the second one. Is negative 6 less than or equal to 4? Sure. Is negative 17 less than 5? Sure. So for this system, actually any point in that shaded region, any point in the shaded region is a solution. There's an infinite number of solutions. So let's just see where you're at. Why don't you pause the video and give this a shot? So your first inequality, I want any point where the y-coordinate is greater than 3. So if you graph the line y equals 3, it'd be somewhere along here. Now I'm dotting it because I only want where y is greater than 3. So that tells me I'm actually not including any points on that line y equals 3. I only want points above where y is greater than 3. So this is kind of the look for the first inequality. If you graph the second inequality, maybe you went through and solved for y. So if I graph the line y equals 9 halves x plus 8, I'd start at 0, 8. And then plot your slope, up 9 over 2 or down 9 left 2. And now, should I make this line solid or dotted? Well, I want anything that's less than or equal to. So I want to include all of these points because these points would be where the y value equals 9 halves x plus 8. And then I want anything less than that. So anything less than that would be in this region. Now, maybe you're having trouble deciding which side to shade when it says less than or equal to. I always kind of think of it as if I took this line and I needed to tilt it to make it horizontal, the quickest way to make it horizontal would be to tilt it to the right. That's what side I should be shading on. To the right is kind of the below. So that's one way to think of it. Or again, if you're not sure, just plug in the point 0, 0. So if I plug in 0 for x, 0 for y, let's see, I'd have 0 is less than or equal to, well, if x was 0, this stuff would go away. Is 0 less than or equal to 8? Yes, it is. So kind of this is where I would shade to graph that second inequality. Now, it looks like I already kind of went through and graphed the solution to the system, if you caught it. So where's the overlap? That's the part in the upper right corner. So if I erase everything else, and I erase all of this stuff, any point in that overlapping region would make both inequalities true. So for example, I don't know, the point 6, 7 would be one possible solution. If I plugged in 6 for x, 7 for y, both inequalities would be true. Now, just a check for understanding, is the given point a solution to the system of inequalities graphed below? So let's look at the first one in purple. Negative 4, 2. If I look at this point, that would be right here. Is that a solution to the system? No way, it's not in the shaded region. So that would not be a solution to the system. Negative 4, negative 2, the orange point. Would that be a solution? Yes, it would be. It's in the shaded region. So that would be yes. 3, 0. What do you think? 3, 0, is that a solution? This is actually a no, it's on the dotted line. So the points on the dotted line are not included in the solution set. Negative 2, 0. So what if I am on the solid line? That would be a yes. Any points on those lines are included on a solid line, is included in the solution set. And 4, 3. So 4, 3 is up here. Is that in the solution set? No. And actually, what did I just say? Any point on the solid line, but it has to be in this shaded region. So anything down here, yes. But out here, this might make that first inequality true, but it would not make the second inequality true. So that's kind of not in the overlapped region that's being shaded. So 4, 3 would be a no. It would make one inequality true, but not the other. Another way to do this problem would be to actually write the equation for the system. So I have two inequalities. One of them has a y-intercept of 1, rising 1, running 2, and I'm shading below. It's a solid line, so that would be the inequality y is less than or equal to 1/2 x plus 1. And then on the second, since I have a dotted line and I'm shading beneath, it's going to be y is less than, your y-intercept's up at 0, 3, and your slope is -1, down 1 over 1. So that gives you your second inequality. If I find the inequalities, then I could actually just plug in this for x, this for y, and see if they make both inequalities true. If these points don't make both inequalities true, then they would not be a solution to the system. Okay, last example. Maybe you've been watching the Simpsons marathon. Meister's Pizza Emporium charges $1 for each vegetable topping and $2 for each meat topping. You want the Homer special, which is at least 5 toppings. You have $10 to spend on the toppings. How many of each type of topping can you get on your pizza? There's a lot of information here, but let's just key in on that last part. Really what I want to know is how much of each topping. So let's let V equal the number of veggie toppings. And then let's just have M equal the number of meat toppings. And I would strongly encourage you to take some notes on this. This is probably the trickiest example and maybe a new piece that you didn't study in the past. Essentially, I need to write a system of inequalities that describes the situation. So what are the restraints on the situation? Well, if I see, I mean, I've kind of got a money restraint. I only have $10 to spend. And each veggie topping is $2, and each each meat topping is $2, and each veggie topping is $1. So if I'm writing an equation to relate the price, well, $2 times the meat toppings, so $2 for every meat topping, and then I'm going to pay $1 for every veggie topping, or just V. That has to be less than or equal to $10. So however many meat toppings I buy times $2, however many veggie toppings times $1 has to be less than or equal to 10. That's all the money that I have. Then it also says I want the Homer special, which is at least 5 toppings. So if I want to pick 5 toppings, the number of veggie plus the number of meat toppings has to be at least 5, so greater than or equal to 5, and I'll be happy. Now there's really 2 other inequalities I'm going to throw in here, and this one people sometimes forget. This can't be negative, so I can't have a negative number of toppings. So V should be greater than or equal to 0, and the number of meat toppings should also be greater than or equal to 0. So there's kind of 4 different inequalities that I'm looking at. If I want to graph this inequality, these last 2 right here, these last 2 inequalities really show me that I'm going to be dealing in quadrant 1. And I don't know if you remember graphing, but quadrants 1, 2, 3, 4. Quadrant 1 is where x and y are positive, or in this case, m and v. So if I'm graphing, these last 2 inequalities are maybe where I'm going to start. So just label, I just chose meat as the x-axis, veggies as the y-axis. I could switch those around, it doesn't really matter. So if meat's on the x-axis, that'd be like, this would almost be like saying x is greater than or equal to 0. If you were graphing that, here's the line x equals 0, and I would shade anywhere to the right. And then if v's the y, if this is on the y-axis, this would be like saying y is greater than or equal to 0. So anywhere, here's the line y equals 0, and I'd shade anything above. And where's the overlap? The overlap's really in quadrant 1. So just for the sake of not making this too messy, just note that my solution set should be somewhere in quadrant 1, so I'm going to erase the shading. Then how do I graph everything else? Well, it might be easiest just to use your x and y intercepts. So let's look at our first inequality. So mv, if I plug in, and meat is like the x, v is the y, if I plug in 0 for m, well, 5 plus 0 equals 5. If I plug in 0 for v, 5 plus 0 equals 5. So 0, 5, 5, 0. If I graph, this would be the line v plus m equals 5. So if I want anything greater than or equal to 5, I'd want to shade this region. So this point right here would be saying, well, maybe I have 4 meat toppings and 2 veggie toppings. That would be acceptable. That adds to a number greater than or equal to 5. Another way you could graph the inequality is just to solve for the v or the y, whatever's on the y-axis. So your slope is -1, and you're starting at your y-intercept of 5. Similarly, you could graph the very first inequality by finding the y-intercept and x-intercepts by plugging in 0 for x, 0 for y, or you could solve for v. Note that the slope is -2 and your y-intercept is 10. Either way, this is the graph of the line v plus 2m equals 10. If I want v to be less than or equal to, I want to shade anything below. So anything down here. But if I look at where the overlap would be, the overlap is really just going to be anything kind of in this region. Now the last thing that I want to point out is this is a discrete example, meaning there's a countable number of answers. I can't have 2.3 meat toppings on my pizza. Unless if I was doing half and half, I guess. But let's just assume I can't have any fractions. So if I were actually graphing this, I should probably only include coordinates with whole number values. So for instance, one solution would be this point right here, where you would order 1 meat topping and 7 veggie toppings. That would cost, what, $9? You still have at least 5 toppings. You've met your requirements.